Good morning everyone. Welcome to this first video lecture of a discrete math course. Today we're going to learn about mathematical induction. This is a topic which we have been studying since last two lectures. We're going to look at some more proof example and then we're going to conclude this topic. Let's suppose if you want to prove a statement P of n, where P of n, it could be any given propositional function, and if you want to prove that P of n is true for all positive integers n, then you can use this simple mathematical induction, which includes two steps, and the first step is your basis step. In the basis step, since you have to prove this statement P of n, which is true for all positive integers, so my base case is going to be n is going to be 1, is the first positive integer. So the first thing in the basis step, I have to verify that P of 1 statement is true. Then I move to my inductive step, and in my inductive step, I assume the hypothesis that my given statement is also true for an arbitrarily positive integer k, and it should be clear that in the hypothesis of my simple mathematical induction, I assume my P of k statement is true for an arbitrarily positive integer k. It's not that we have to put the hypothesis that this statement is true for all positive integers k. Okay. Then in the inductive step, we have to prove that if P of k is true, then P of k plus 1 is also true. So under the hypothesis of P of k, which we assume in the hypothesis true, then we have to prove that the P of k plus 1 is also going to be true. And by following these two steps, we can conclude that the given statement is true for every positive integer n. In terms of simple rule of inferences, we can say that my premises here is going to be P of 1 if P of 1 is true and for all k. If P of k implies P of k plus 1, if that also becomes true from your inductive step, then we can conclude that the statement is going to be true for every positive integers n. When we look at the structure of the strong mathematical induction, then a strong mathematical induction also holds two steps. So first is your basis step, and let's suppose we want to prove the same statement P of n for all positive integers n. So in my basis step, I have to verify the base case, which is my first positive integer corresponding to n is equal to 1. So I have to verify that P of 1 is true. Then in my inductive step, my hypothesis is going to be more strengthened, and I have to assume that instead of assuming that my statement is true for an arbitrarily k, now I'm assuming that my statement is true for every j, and j could be starting from your base case, starting from 1 and all the way up to a k positive integer. Okay. And under this hypothesis, in my inductive step, I just have to prove that if P of 1 is true, P of 2 is true, and all the way up to P of k is true, then this implies your P of k plus 1 is also true. Which, based on my rule of inferences, I can say I have the premises, which is P of 1 is true and P of 2 is true and all the way up to P of k is true, and if they implies P of k plus 1 is also true for an positive integer k, then I can conclude my statement that for every n, P of n statement is true, where n is a positive integer. So if you look at these two structure of a simple mathematical induction and the strong form of the mathematical induction, so there's some useful facts you can look at here. So the mathematical induction and the strong induction, they only differ in the inductive hypothesis step. The strong induction can be viewed as the standard mathematical induction with a more strength inductive hypothesis. But since they are concluding the same conclusion is that the statement is going to be true for every positive integer. So the mathematical induction and the strong induction, they both are equivalent. The strong induction is also called as the second principle of the mathematical induction, or sometimes we call as the complete induction. If you just want to compare the simple mathematical induction with the strong mathematical induction, you can put an analogy that the simple mathematical induction is a screwdriver and a strong induction is basically the power, but with more power, which is going to be a power screwdriver. But they both are doing the same task. Okay, so that's the reason they are equivalent. The strong induction is preferred over simple mathematical induction because sometimes it's easy to write the proof by using the strong induction structure in comparison to your simple mathematical induction. In today's lecture, we're going to look at some examples where we're going to apply both the techniques in writing the proof of that statement so that you can clearly see the difference between both the techniques. Let's suppose we take the first example and we want to prove that if n is an integer greater than 1, then it is either a prime number or can be written as the product of primes. Now we're going to apply both of our techniques by using the simple mathematical induction and by using the strong induction and see how we can write the proof for this case. So when we look at the proof by using the simple mathematical induction, the first thing we can define P of n statement as n is either a prime or can be written as the product of primes, where my domain is all integers where n is greater than 1. Now the basic step here, my first integer in my domain is n is equal to 2, and since 2 is a prime number, then my statement P of 2 that becomes true. If you look at the inductive step of my proof, then I start with the hypothesis and assume that this statement P of k is true for an arbitrary integer k where k is greater than 1. That means I'm assuming that k is either a prime or can be written as the product of primes. Now in the inductive step, under this hypothesis, I have to prove that for every k, if P of k is true, then P of k plus 1 is also true. That means I have to prove that if k is either a prime or a product of primes, then k plus 1 is either a prime or product of primes. But the hypothesis which I have assumed here under this simple mathematical induction is not going to be useful in proving the statement for k plus 1. So I somehow stuck there, and you can write the proof of the same theorem by using a strong mathematical induction, which will be a easy way to write this proof. So we stop our simple mathematical induction based proof here, and our claim is then the claim here is that this proof is much easier to write by using the concept of strong induction. So let's look at the strong induction proof now. The basic step of my strong induction is going to remain same as in the case of simple mathematical induction before. So for n is equal to 2, since 2 is a prime number, so P of 2 is going to be true. In the inductive step of my strong induction, I put my hypothesis that assume that for any value of j starting from 2 up to k, my P of j statement is true. That means for j in between 2 to k, j is either going to be a prime or is going to be a product of primes. Now under this hypothesis, I have to prove that my P of k plus 1 statement is true, where pk plus 1 is the statement that k plus 1 is either a prime or product of primes. So the two cases will appear here. The first case is when k plus 1 is a prime. If k plus 1 is a prime, then my statement P of k plus 1 is true. So it's going to become a valid statement. The second case is corresponding when k plus 1 is not a prime. That means k plus 1 is going to be a composite number. Then by definition of the composite number, k plus 1 can be written as the product of p and q, where p and q are the positive integers in between 2 to k plus 1. or we can also say P and Q are the positive integers starting from 2 all the way up to k. Since P and Q are integers, it's going to have a value at least 2 and not exceeding k. So we can use our hypothesis to write that P and Q are product of primes. Thus we can conclude that k plus 1 is written as the product of primes, and this implies P of k plus 1 is true. Then by following the strong induction, we proved here that P of n is true for n greater than 1 integer. Sometimes it's not easy to write the proof of any given mathematical statement by using your simple mathematical induction, but it becomes easy to write the proof of such a statement by following your strong mathematical induction structure. Now we're going to look at another example where we're going to learn about more number of base cases, and that proof can be written by using both the technique of weak mathematical induction as well as the strong mathematical induction, and then we can compare the pro and cons of both the techniques. Our next problem is based on the example. Let's suppose if we want to figure it out which positive integers can be written in terms of 4 and 5 or in terms of non-negative multiples of 4 and 5. Then if you look at 1, we cannot represent 1 in terms of 4 and 5. 2, we cannot represent 2. 3, we cannot represent 3. 4, we can write 4 as 1 times 4. 5 can be written as 1 times of 5. 6, we cannot represent 6. 7, we cannot represent 7. 8, we can write 8 as 2 times 4. 9, we cannot represent 9. 10, we can write 10 as 2 times of 5. 11, we cannot represent 11. 12, we can represent 12 as 3 times of 4. 13, we can represent as 2 times of 4 plus of 5. 14 can be represented as 2 times of 5 plus of 4. 15 can be represented as 3 times of 5. 16 can be represented as 4 times of 4. 17 can be represented as 3 times of 4 plus of 5, and you keep doing so. So what did we learn from here? So we learned through this example that if you consider all positive integers after 12, okay, so all positive integers after 12, they can be written as a non-negative multiples of 4 and 5. And this is going to be our next theorem. So the statement of our next theorem is prove that every integer n greater than or equal to 12 can be written as 4 times of a plus 5 times of b for some non-negative integers a and b. So our first proof technique is based on simple mathematical induction, where we define our P of n statement that n can be written as 4 times of a plus 5 times of b for some non-negative integers a and b, and the domain where I supposed to prove this statement is going to be all integers where n is going to be greater than or equal to 12. So our basis step in this case is n is equal to 12. So 12 can be written as 3 times of 4 plus 0 times of 5, where the value of a and b could be 3 and 0, which are the non-negative integers. So since 12 can be written as a combination of 4 and 5, so P of 12 is a true statement. In our inductive step, our hypothesis is that for an arbitrary integer k greater than or equal to 12, assume that P of k is true statement. That means k can be written as 4 times of L and plus 5 times of M, where L and M are non-negative integers. Now we need to prove that for every integer k greater than or equal to 12, if P of k statement is true, then under this hypothesis, my P of k plus 1 statement is also true. So for k plus 1 integer, where k is greater than or equal to 12, there will be two kind of cases will happen. If you look at your example, then for all integers greater than or equal to 12, you will see two kind of cases. The one case where the 4 will not appear, and the another case where the 4 will appear at least once in all those remaining cases. So we're going to use these facts in building two cases in our proof. So our case first is corresponding to the case when k is going to be greater than or equal to 12, and k is representing by 4 times of L plus 5 times of M, where the value of L is going to be greater than or equal to 1 and M could be any non-negative integers. And we're going to make sure here that at least one of the 4 is used in building this k. Thus we can represent k plus 1 as 4 times of L plus 5 times of N plus of 1, when we substitute k is going to be equal to 4 of L plus 5 of M. So this we can rewrite as 4 times of L plus 5 times of M, and 1 we can represent as 5 minus 4. And if we simplify, then k plus 1 can be represented as 4 times of L minus 1 plus 5 times of M plus 1, where L and M, they having a value greater than or equal to 1 and M is greater than or equal to 0, and they are the integers. So we can rewrite our k plus 1 as 4 times of L prime plus 5 times of M prime, where L prime is defined as L minus 1, which is greater than or equal to 0, and M prime is defined as M plus 1, which is also greater than or equal to 0, and they are the integers. So this implies that P of k plus 1 is true here. Our second case is corresponding to k greater than or equal to 12 integers, and there is no 4 used in representing that integer k. So k can be written as 4 times of 0 plus 5 times of M, where the value of L is going to be 0, which is a fixed value here, and M is going to be any non-negative integer. So in this case, k can be written as 5 times of M. Since k is greater than or equal to 12, so we need at least 3 5 to represent the integer k. Thus k plus 1, which is going to be the next integer, can be replaced by 4 4s instead of like the k integer which was represented by 3 5. The k plus 1 can be replaced by 4 4s, and this is an example of k. So k could be 15, which can be represented by at least 3 5. So k plus 1, it will become 15 plus 1 16, and 16 can be represented by 4 4s. And by using this fact, we can say our statement P of k plus 1 is true. Thus, by following the mathematical induction, we proved that for every integer greater than or equal to 12, n can be written as 4 times of a plus 5 times of b, where a and b are non-negative integers. So if you go over the proof by using a simple mathematical induction, our statement was that for every integer n greater than or equal to 12, n can be written as 4 times of a plus 5 times of b for some non-negative integers a and b. We wrote the proof by using a simple mathematical induction. We define our P of n statement, where n can be written as 4 times of a plus 5 times of b for some non-negative integers a and b. My domain was all integers greater than or equal to 12. My basis step was for n is equal to 12. 12 can be written as 3 times of 4 by using 3 4s, and P of 12 becomes a true statement. when it comes to the inductive step, I assume my hypothesis, and my hypothesis, I assume that for an arbitrarily k integer which is greater than or equal to 12, assume that p of k is true. That means k can be written as 4 times of L plus 5 times of M for some non-negative integers L and M. Now to prove my inductive step, that if p of k statement becomes true, then p of k plus 1 also becomes true, and k is greater than or equal to 12 is going to be the integer. Then for k plus 1 integer, when k is going to be greater than or equal to 12, there will be two cases arises here. The first case, when the k integer in my hypothesis step is written with the help of at least one 4 used. So if k can be written as 4 times of L plus 5 times of M, and L has a value greater than or equal to 1, and M could be any non-negative integers, then k plus 1 you can resimplify, and you can show that k plus 1 can also be written as 4 times of L prime plus 5 times of M prime, where L prime and M prime, they are both non-negative integers. So my statement p of k plus 1 statement becomes true here. The second case, when my hypothesis k is written, but I have not used any 4 there, so that means the k is purely written in terms of a multiple of 5. Since k is going to be greater than or equal to 12, so we need at least 3 5s to represent my k, and the first case corresponding to k, which can be written only with the help of multiple of 5, is 15. So if in my hypothesis I have assumed that the k is written purely based on multiple of 5, and for this example, for k is equal to 15 is written multiple of 3 5s, then k plus 1 can be written as instead of 3 5s, you can write k plus 1, which is 16, as 4 4s. Okay, so my statement still becomes true because I am able to represent k plus 1 as a non-negative multiple of 4 and 5, and by using my mathematical induction, we proved this statement that n can be written as 4 of a plus 5 of b, where a and b are non-negative integers, and n is greater than or equal to 12, which is also an integer. Now we're going to write the second proof of the same statement by using the concept of strong induction. So my basis step, in case of a strong induction, I can write for n is equal to 12. 12 can be written as 3 times of 4 plus 0 times of 5. So this becomes true. N is equal to 13. 13 can also be written as 2 times of 4 plus 1 times of 5. So my statement becomes true. For n is equal to 14. 14 can be written as 1 times of 4 plus 2 times of 5. And similarly, 15 can be written as 0 times of 4 plus 3 times of 5. So my statement for n is equal to 12, 13, 14 and 15, they becomes true. So this is an example of a strong induction where we're going to generalize the concept. We are going to have more than one base case in my basis step. So right now we have the 4 base case in this example, and I will explain it later why we choose these 4 base cases. In my inductive step of my strong induction hypothesis, so I'm going to assume that suppose for every j greater than or equal to 12 and less than or equal to k integers, j can be written as 4 times of L plus 5 times of M, where L and M are non-negative integers. Now to prove the statement for n is equal to k plus 1, we can write as k plus 1 is going to be equal to k plus 1, which you can rewrite as nothing but k minus 3 plus of 4, and which is nothing but your k minus 3 and plus of 4. Okay, so this side is going to remain k plus 1, this side is going to remain k plus 1. So we have rewritten k plus 1 is nothing but the combination of k minus 3 and plus 4. Now we can use our inductive hypothesis for k minus 3. So based on the inductive hypothesis, we can say k minus 3 can be written as 4 times of L plus 5 times of M, where L and M are non-negative integers. Now if you replace the value of k minus 3 in this equation, so k plus 1 can be written as 4 of L plus 5 of M plus of 4, which you can rewrite as nothing but 4 times of L plus 1 plus 5 times of M, and this implies that my statement P of k plus 1 is true. Now if you look at your inductive hypothesis, where you have used that k minus 3 can be written as 4 times of L plus 5 times of N, here you have used this condition that k minus 3 is greater than or equal to 12, and this implies that k is going to be greater than or equal to 15, and this implies that k plus 1 is going to be greater than or equal to 16. Okay, so we are analyzing this case to prove the statement for k plus 1, okay, when k plus 1 is greater than or equal to 16. And because of that, we're going to cover all our cases of 12, 13, 14 and 15. We're going to include all those cases in our basis step. Okay. Because then only you can use this inductive hypothesis in proving your statement for k plus 1. And on basis of that, you're going to decide how many number of base cases you should have in your proof.